In this short section, we'll be looking at iron and calcium absorption in the GI tract. In this section of the GI physiology module, we'll be discussing iron and calcium absorption. Two forms of iron are ingested, namely free ionized iron and iron bound to hemoglobin and myoglobin. This is referred to as heme iron. Free iron in the diet is in the form of Fe3+ or ferric, and is changed to a ferrous or Fe2+ form for absorption. There are various dietary factors that affect the availability of free iron for absorption. These include phytic acid, phosphatases, and oxalates. And ingested iron is absorbed in the duodenum. Iron is absorbed across the apical membranes of the intestinal epithelial cells in the form of free iron, Fe2+, or as heme iron, which is iron bound to hemoglobin or myoglobin. Inside these intestinal cells, the heme iron is digested by lysosomal enzymes, releasing free iron. Free iron then binds to apoferritin, is transported across the basolateral membrane into the blood. For transport, iron is bound to transferrin, which is a beta globulin, and it transported from the small intestine to its storage sites in the liver. From the liver, iron is transported to the bone marrow, where it's released and utilized for synthesis in hemoglobin. So the important thing to remember is that free iron in the diet is ferric or Fe3+ iron, but for absorption it's changed to Fe2+ or ferrous iron. As far as calcium absorption is concerned, 30 to 80% of ingested calcium is absorbed depending on the body's needs. And unlike iron, which is only absorbed in the duodenum, all portions of the small intestine actively absorb calcium. Calcium is an important mediator of second messengers and metabolic regulators. It's essential for the excitation process of skeletal, smooth, and cardiac muscle, as we discussed in earlier modules. Its absorption is regulated by vitamin D and parathyroid hormone, and is matched to dietary intake, urinary excretion, as well as plasma levels. So calcium is absorbed in all parts of the small intestine and depends on the presence of the active form of vitamin D, known as 1,25-dihydroxycholecalciferol, otherwise known as calcitriol. Dietary vitamin D, which is just cholecalciferol, is inactive. In the liver, cholecalciferol is converted to 25-hydroxycholecalciferol. The easy way to remember this is that the liver has multiple functions, therefore it takes up the role of 25-hydroxylation of vitamin D3 or cholecalciferol. This 25-hydroxycholecalciferol is the main circulating but inactive form of vitamin D. In the proximal tubules of the kidneys, one hydroxylation takes place, so then you have the active form of vitamin D, which is 1,25-hydroxycholecalciferol. This process is catalyzed by 1-alpha hydroxylase. So now this active form, the 1,25-dihydroxycholecalciferol, is the biologically active metabolite of vitamin D. It has a number of actions, namely to promote calcium absorption from the small intestine, and it does this by inducing the synthesis of vitamin D-dependent calcium binding protein, or calbindin D, in the intestinal epithelial cells. When there's vitamin D deficiency, there is a failure to convert vitamin D to 1,25-dihydroxycholecalciferol. This can occur, for example, in chronic renal failure when 1-alpha hydroxylation does not take place. Inadequate calcium absorption takes place from the GI tract. In children, inadequate calcium absorption presents as rickets, and in adults it presents as osteomalacia. So this diagram just shows you an overview of what happens with calcium absorption. Vitamin D3 undergoes 25-hydroxylation in the liver, and then 1-hydroxylation in the kidney to form 1,25-dihydroxycholecalciferol. This then promotes in the small intestine the synthesis of calbindin D protein or calcium binding protein, which promotes absorption of calcium. Low calcium levels also result in the stimulation of release of parathyroid hormone, which promotes formation of 1,25 dihydroxycholecalciferol and subsequently increased absorption of calcium from the GI tract. In the last section, we looked at iron and calcium absorption in the GI tract. It's important to understand that iron is only absorbed in the duodenum and calcium can be absorbed throughout the gastrointestinal tract.